张 slide，OK，所以今天可能上不完这一张 ，OK， 但是应该会接近上完，所以我们下一次可能要等到下礼拜我回来，才能把这一张完全上完 ，OK， 所以我们大概就是比我想象中的要久，但是就像我讲的 ，OK， 之后的每一个 chapter 大概都需要上2次或甚至2次以上，所以这个是很正常。每一个 chapter 如果说是30章到40章之间，那我们通常一次可以上完。那这一章要有88张 slide， 所以本来就一次就是2次就是很难上完 ，OK， 所以跟我估计也差不多啦，一堂课大概上就3个小时，大概上35章左右，所以我们大概可以上到70章 ，OK， 70章左右 ，OK， 我们现在已经在第47章 slide，OK， 跟我的估计的速度其实是差不多的 ，OK， 好 ，Anyway， 不对，为什么讲中文？Okay. So back to English now. Okay. Sometimes I have trouble like switching between Chinese and English. Anyway, okay. Okay. Let me rephrase. What I just said in English. Okay. What did I say? Okay. We are on the 47th slide. Okay. Now. Okay. Originally, I hope to be able to finish this chapter in 2 lectures, but it looks like I will not be able to do that today. Okay, because we still have 42 slides. Okay, which is very unlikely that we can finish 42 slides in 2 hours. Okay, but as I said, okay. In one lecture, we normally can finish slides around 30 to 40, around 35 slides. Okay, so for 2 lectures, we should be able to finish around 70 slides. Okay, so we are on the right track. Okay, to finish 70 slides. Okay, so that's not an issue. But the issue is, we have 88 slides for this chapter, okay? So I estimate that we will need another hour or so, okay, to be able to finish this chapter. So most likely we will finish this chapter in another 2 weeks after I come back from China, okay? But anyway, okay, just want you to know that we are still on the right track. Okay, it's not like we have delayed or something. Okay, it's just okay. I already told you. Okay, starting from this chapter, okay, each chapter will be very heavy. Okay, so it is natural. Okay, to have 2 or even more than 2 lectures for one chapter. Okay, so anyway, okay, so we just talked about the likelihood function, okay, for 2 coin scenario, okay, it's like this, right? So how about the posterior, okay? For the posterior, okay, the posterior distribution of our belief about underlying bias is derived in the usual way by applying Bayes' rule. So it's like this, okay? So it's this one divided by the integration of this, right? So this one is our prior, right? P theta 1 theta 2 is the joint probability of theta 1 theta 2. That's our prior, the joint prior probability. Okay. So the theta j and this one is our likelihood function, which is this one. Okay. So the theta j's left side of the equation are in the numerator of the right side are referred to specific value of theta j, but the theta j's in the integral in the denominator range over all possible values of theta 3. What I'm talking about here is, okay, this theta 1, theta 2, okay, will be the same as theta 1, theta 2, theta 1, theta 2 here. But this theta 1, theta 2, okay, in the denominators, okay, this theta 1, theta 2, theta 1, theta 2, theta 1, theta 2 are variables, okay, are variables, okay. So in order to avoid like confusion, you may want to add a star, okay, here, just to make sure you are not confusing this theta 1, this theta 1 are the same as this theta 1. No, they are different. They are different. This theta 1, theta 2 will be the same as theta 1, theta 2 in the numerator. But in the denominator, okay, the theta 1 and theta 2 are simply variables. Okay, are simply variables. Okay, so even though we are using the same name, it doesn't mean they are the same thing. Okay? So, okay, here we could use the conjugate prior. Okay, use beta distribution as conjugate prior again. Okay, so this basically, okay, this P of theta 1, theta 2, this posterior, okay, this posterior equal to this one, okay, and you can apply, this is the likelihood, right? We just apply likelihood function here, okay, and then we have P theta 1, theta 2 divided by P of D, okay, and then we apply the, because P theta 1, theta 2, okay, according to our independence assumption, the P theta 1, theta 2 we know P theta 1, theta 2 is the same as P theta 1 times P theta 2, right? Right? And then we can use our, beta prior, okay, the beta conjugate prior, okay, for theta 1 and theta 2. So we use this, you can see here, we are using this one. This is the, for the conjugate prior for theta 1, it's going to be theta 1. This one is going to be theta 1 to the power 1 minus a times, a minus 1. Keep that trouble putting them in opposite manner. Times, okay, 1 minus theta 1. Oh, this is A1, because now we have two A and two B, so we have to put A1, and this is B1 minus 1, and divided by capital B, A1, B1. Okay, so this is, you can see these terms here, right? And the other one is this one. This one is going to be theta 2, A2 minus 1 times 1 minus theta 2, B2 minus 1, okay, capital B, A2, B2, okay? And you can see it here, this one. Okay? And then we still have evidence here, right? And then, for similar, and then with some additional like massage, okay, very simple algebraic arrangement. This is what we have. Okay, we just combine like the exponent which have the same underlying like a term. Okay, so for all the exponent for theta 1, we put it together. For all the exponent for theta 1 minus theta 1, put it together, and so on. Okay, that's the result. Okay, so that's the result so far. Any question? So far so good, right? Okay. Then, again, this is posterior, right? This is posterior. So if I do it should be we should result in 1, right? Because it's posterior. So posterior is the probability distribution, right? Any question? Right? I hope this is this is agreeable by everybody, right? Okay, we all know prior is a probability distribution, and the posterior is probability distribution. So you do the integral over prior or over posterior, you always get 1. Okay, you always get 1. And I have just shown you this one equal to that long and ugly stuff, right? 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 So I can replace the middle part with this term, right? Well, we have theta 1 something here. 1 minus theta 1 something here. Theta 2 something here. 1 minus theta 2 something here. Right? I'm just too lazy to write them down. Okay. Okay, but you get an idea, right? And for the denominator, we have P, B, and the capital B, A1, B1, capital, and then multiply. Capital B, A2, B2, right? D theta 1, D theta 2 equals to 1, right? 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 So, I have told you repeatedly, okay, this is a constant, right? This evidence is a constant, right? Right? And this capital B, A1, B1, because A1, B1 are constant, right? They are the parameter for prior. So when the prior is given, A1, B1 will be fixed, right? So since A1, B1 are fixed, so capital B, A1, B1, of course, will be a constant, right? Okay. The same thing can be said for capital B, A2, B2, right? So this is constant, this is constant, this is constant. The product of 3 constant, well, it is still constant, right? Okay? since the denominator is pretty much a constant, so we can somehow like, we don't need to put them inside the integral, right? We can put them out, right? So, in other words, double integral, okay, theta 1, da 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 da, 1 minus theta 1, da 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 da, theta 2, da 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 da, 1 minus theta 2, da 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 da, d theta 1, d theta 2, okay, divided by p d b a1 b1 b a2 b2 equal to 1, right? Right? So it actually tells you that this constant will be the same as the result of this integral, right? This constant will be exactly the same as the result of this double integral, right? Right? Okay, so what is this double integral, by the way? This double integral, okay, by the way, when you try to do integration for theta 1, this part is constant, right? Because these two terms involve only theta 2, right? Right? Okay. When you do integral over theta 2, I'm sorry, I forgot to put theta 2, 2 here. Okay. When you do integral over theta 2, this theta 1 again becomes a constant, right? Okay. So I can rewrite this double integral into something like this. Integral theta 1 da 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 1 minus theta 1 da 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 d theta 1 times integral theta 2 da 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 1 minus theta 2 da 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 d theta 2. I can kind of like break it into two parts. Because when you do d theta, when you do integral over theta 1, theta 2 can be considered constant. When you do integral for theta 2, when you do the integral over theta 1, theta 2 can be considered constant. When you do integral over theta 2, theta 1 can be considered constant. So you can break them into two parts. Okay, so this will be the same as this one, right? Will be the same as this denominator here. So what will be this, by the way? If you look closer, this thing will be this one. This part is, according to definition, of course, is this capital B, this. And this second part here, according to the definition of capital B, is this one. Okay? So when you put them together, okay, when we put them together, what we are getting, okay, basically, okay, is like it's this one, okay, it's beta theta 1, z1 plus a1, comma, n1 minus z1 plus b1, times beta theta 2, z2 plus a2, comma, n2 minus z2 plus b2. It's going to be just like, what should I say, like you break them into two different, well, you can, because you can kind of like, you consider each coin separately. and you do the posterior, and then you multiply them together. Okay? Because when you consider only one coin, now everybody knows how to do this with a conjugate, right? With a conjugate plier, right? Okay, but interestingly, okay, if you consider like the biases of two coins, okay, it's going to be exactly just like you do like a biases of one coin, you know, separately, and then you multiply them together. Okay, so that's something very interesting here. Okay. Of course, like the textbook uses a different way to discuss this, but I will skip that part. Okay, if you are interested, you can see like how the textbook explain how this thing is obtained. But basically, I use my own way to describe that. Okay. So let's recap what we just discussed. When the prior is a product of independent Bell distribution, the posterior is also a product of independent Bell distribution. With each Bell obeying the update rule we derived in chapter 6, in the previous chapter. Okay? So maybe it's a surprising result, or maybe it's not. Okay? After all, we assume the independence of all these between two coins, and you know, and between like a flip of each coin, we assume the independence of all these. Okay, so so that's our result. But you may wonder, like, hey, wait a moment, aren't we supposed to discuss Gibbs sampling? Why are we still discussing country prior here? Right? This, at the beginning of this class, today's class, I'm talking about like we are going to discuss Gibbs sampling. I actually mentioned like well, Metropolis algorithm it's good, but it's inefficient, right? So we need to talk about Gibbs sampling. But so far, all I have talked about is applying country prior on two coin scenario, right? Why do I do that? Because, okay, I need to establish like the ground truth for like for some example with like more than one parameter. Okay, more than one parameter. In this case, it's two parameters, right? Because remember, I told you guys like the Gibbs sampling works when you have more than one parameter, right? And when we talk about like Metropolis algorithm, I try to compare the result with the country prior result, right? Because well, with the country prior, only with the country prior I can have like the ground truth, like a posterior, right? So I can make comparison, right? Okay. So now, okay, before I discuss like a Gibbs sampling, at least I have to have a tool, okay, to derive like a ground truth, okay, ground truth result, okay, accurate result, not just approximation, accurate result for situation, for scenario that has more than one parameter. And so far we have done that, okay. So I have shown that, okay, we can use country prior, okay, to discuss like biases of two coins, okay, and now with that in mind, okay, we can establish a ground truth, okay, from like a two coin scenario, and then we can now discuss like Gibbs sampling, okay, but of course, I mean before that we still need to show you a little bit, okay, of like the result, like this country prior. Okay, so this is like we can visualize posterior distribution of two coins So we want to plot the probability densities as the function of two parameters, theta 1 and theta 2. Okay? So prior begins with beta theta 2 2 distribution for both biases. So you can see, okay, this is like a prior. Okay, so you can see this is like kind of like a, yeah, the center is you have like a what should I say? The mean is because you can see like it's a 2 2, right? 2 2. So which means like the so it's for both theta 1 and theta 2, 2 2. So it's first it's a symmetric, right? You know it's symmetric. Okay, it's symmetric, and also like the center will be the mean. Okay, the center will be the mean, and because the A and the B are both 2, so it's not, the kappa value is kind of low. Okay, so it's not that okay, it's not that narrow. Okay, so you can see like a mild curve. Okay, or a mild like a bulge. Okay, in the center here. Okay, this one just show you like shoot, I forgot the English term for that. 等高线. What's the English term for that? Okay, this one shows like where there's like the same y value. Okay, same y value. You can see the highest place is here. Sometimes we use this one to describe like a mountain, right? Okay, I forgot the English term for that. I only know Chinese term. Okay, shoot. Previously, I remember what the term is. Okay. But anyway, okay. So you see the point. Okay. Okay. If you have like these lines are closer to each other, it means you have more. The center is more concentrated. You have more concentrated center. Okay. But now because it's as I said, it's a mild prior, so it's a little bit like not too close to these lines are not close to each other. Okay, and then okay, the data is z1 equal to 6. So you flip the first coin for 6 times, you get 8 times, you get 6 heads. You flip the second coin for 7 times, you get 2 heads. So what you are going to get is can somebody tell me what the posterior is going to be? Okay, it's going to be beta theta 1. What's that? Z1 is 6, right? So it's going to be 2 plus 6 and 2 plus number of tail, right? For the first coin, right? How many tails do we have? 8 minus 6, right? So we have 2 here. Times beta theta 2. Okay? Again, originally we have 2. Okay? How many heads do we get? 2, right? Z2 is 2, right? So 2 plus 2. And then another 2 plus, how many tails do we have? 7 minus 2 is 5, right? So it's going to be something like this. Okay, or put it, simplify simplify this, we have beta, theta 1, 8, 4, beta, theta 2, 4, 7. Okay? So you can imagine, okay, if you look from like this direction, you fix the theta 2, and you just look at the change of theta 1. It will look like this one. It will look like this one. So in other words, okay, because the A is bigger than B, right? A is bigger than B, what does that mean? It means the max, the mode will get closer to the right side, right? Right? Remember what we discussed for the beta distribution? If you guys do remember, if you forget, check it out, okay? I think we discussed this last chapter or the chapter before last chapter, I forgot. I think it's last chapter, right? Okay, anyway, so you can see that, so the bulge actually, the mode actually appear like closer to this, to the right side. But if you look at it from this side, okay, from the other side, okay, from this side, you will see that, okay, this theta 1 is kind of fixed. Okay? Instead, you are going to see a change of theta 2. So, because B is bigger, B gets bigger. So, you are going to see the highest place actually appear closer to the left side. Left side. Okay. Okay. So, but of course here, okay, you will see, okay, it's here. Why is it here? Okay. If you look at here from this direction, you see like the mountain actually appear on the right side. Okay, which match this one. Which match this one. But if you look from this side, you will see like the mountain actually leaning toward the down, the lower part. That is because, okay, the lower part actually starts from 0. The lower part is not, it doesn't represent 1. It represents 0 for theta 2. Okay? So it's not here, it's here. Okay, be very careful here. Be very careful here. Okay, you may think like this point represents 0, 0. No, it's this point that represents 0, 0. Okay, so be very careful here. Okay. Oh, I'm sorry. This is the likelihood. This is the result. This is the posterior. Okay, but posterior will be almost the same as likelihood because we have very weak prior anyway. Okay, so you can see the posterior is almost the same as likelihood. Okay, I should have looked at this one, but well, these two are almost the same anyway. So we could, okay, for all present purposes, the proposal distribution is a bivariate normal. Okay, we could use a bivariate normal. Okay, in other words, we can use a normal distribution, but now it's no longer one-dimensional. Originally, if it's one-dimensional, everybody knows what it looks like, right? It's a bell shape, right? It's a bell shape, right? Okay, everybody know what the one dimension, I'm probably shouldn't say like one dimensional because the bell shape is two-dimensional. But of course, that means that we have one parameter, okay, and y basically represent the height, right? This is theta, right? And normally it's kind of like this, right? Right? That's normal distribution. But if you have two parameters, what is bivariate normal? Bivariate normal is like this. This is theta 1, this is theta 2. It's kind of like you put a stick, you try to stick this line. This is, you try to imagine this is the steel wire, okay, steel wire. Try to imagine this is steel wire. And then you try to put a stick, okay, try to fix it at this point, at this origin. And then you try to turn it. Turn it. So it's going to be turned like this way, right? So it's going to become like a bulge, right? It's going to become a bulge, right? Like what you get when you got bitten by a mosquito, right? Right? On your skin, right? It's something like that, right? Okay, so that's basically a bivariate normal. Okay? It's a bivariate normal. So you can imagine a one-dimensional normal sticking a pin down vertically through its peak and spinning it around the pin to form a bell-shaped surface. Okay? So notice that proposed jumps can be in any direction in parameter space relative to the current position. Okay, because current position is the delta will be 0. Okay, and then you can jump like any place. It's just like when you get closer, the probability is higher. That's it. Okay, same thing applied for the bivariate normal. Okay, and this is a result when you apply the Charles algorithm for this two-coin scenario. Okay, and you can see, okay, number of proposal, okay, is 50,000, okay, and the number of accepted steps divided by the number of proposed steps is 0.93. When it's 0.93, what does that mean? It means the standard deviation is too small, right? Remember, this value, this ratio is better to be close to 0.5. If it's too high, that means your standard deviation is too big. If it's too low, it means your standard deviation is too high. Okay? So in this case, the proposed standard deviation is 0.02. That means this is too small. Okay? So well, this is probably not a good result. Okay? You can see, okay, how many? I think we have, see, we actually run it for 50,000 steps. But actually, the effective sample size for theta 1 and theta 2 is only like 276, 253. Okay? The combination of both, okay, will be a little bit more than 500. Okay? But you are running this for 50,000 iterations. So it's very efficient, right? So how about if we try to have a better standard deviation? We make the standard deviation to be 0.2. In this case, okay, we still have 50,000 steps, 50,000 iterations. And then you can see this ratio, number of accepted steps divided by number of proposed, is now 0.41. Well, it's not exactly 0.5, right? It's much better, right? It's much better. So you can see that effective sample size for theta 1 has become 6,700. Effective sample size for TR2 is 6,300. So it's much better than the previous one, right? Okay, but the combination of both will still be around like 12,000, right? 12,000. But we have 50,000 iterations. So that's again just like what I estimated. We have like one effective sample size for every 4 iterations, right? So that's, well, it's not that good, right? Not that good. So as I said, we could use the Paris algorithm, but it's just not very efficient. It's not very efficient. So we finally, at the time, at this moment, okay, to discuss the Gibbs sampling, okay? Even at Paris algorithm most efficient, effective size of the chain is far less than the number of proposed jumps, okay? So that's why, okay, we will consider using different MCMC algorithm, okay? Well, one of the MCMC algorithms that will be more efficient will be Gibbs sampling, okay? What is Gibbs sampling? Okay, Gibbs sampling can be especially useful for hierarchical models. Of course, at this moment, you still don't know what hierarchical model is, okay? But let me tell you this, okay? Almost all the real world application, you will have to build hierarchical model. There's almost no real world application that you do not need a hierarchical model. Okay, because hierarchical model is much more, can deal with much more complex scenario, and it can capture much more information. Okay, then like just like a single layer model. Okay, I will explain hierarchical model. Okay. I think after this chapter, I believe. Okay. And Gibbs sampling is a special case of Metropolis Hastings algorithm, by the way. Okay, which is the generalized form of Metropolis algorithm. Okay, actually, Metropolis Hastings algorithm is very efficient. Okay, it's very efficient. It's just it's more complicated, so we will not cover that algorithm in this chapter. Okay, to be very frank with you, okay, this chapter we are going to discuss, okay, Metropolis algorithm, we are going to discuss Gibbs sampling, but in reality, you never need to implement these algorithms. Why? Because, okay, there are software tools that already built, okay, for you. Okay, you only need to provide like a correct like a model setting and the right parameters, okay, into those tools. It will implement all those models, all those algorithms for you automatically. Okay. There are actually 3 famous tools out there. One is called JAX, okay, that we are going to cover shortly. Okay. The second one is called Box. Okay. There are 2 versions of Box. One is called WinBox. You can tell from the name, okay, that it is available under Windows. Okay, and there's another version of Box called OpenBox, okay, which is available in different platforms. But the book, the textbook that we are using, the previous version, actually use WinBox, okay. But later the author decided to drop the box. I think it was because like the open bound is not that stable, but the weak bound, okay, well, it is restricted to only Windows platform, okay, and what should I say? Like, I don't think the author like Windows, Microsoft Windows that much, okay. So of course, the third tool is called STEM, okay, which is also covered in this textbook, but I don't think we will cover STEM, okay, in this class because it's going to be covered at a much later part of this class. Okay, I don't know if we have time to cover that. Okay, anyway, okay, so here, okay, in this chapter, we are going to discuss this algorithm, the concept of this algorithm. Okay, these concepts are important because before you use this algorithm, of course, it's better that you understand the concept, but in reality, you never need to really implement this model, this algorithm by yourself. Okay, so don't worry about if you feel like these algorithms are complicated, don't worry about that. Okay, because you're not going to write any code for that anyway. Okay, so procedure for Gibbs sampling. Gibbs sampling is a type of random walk through parameter space. It's just like with Parse algorithm, it's a random walk process, okay, random walk procedure, okay. But the walk starts at some arbitrary point, and at each point in the walk, the next step depends only on the current position and on no previous position. This one is also similar to the Parse algorithm, okay. Actually, okay, this type of nature, okay, that the decision is only dependent to the previous state, okay, not on like a previous step, okay, is called remember this chapter is called MC, right? Okay, one of the MC that we discussed is Monte Carlo, right? Okay, the second MC we haven't talked about, right? The second MC is called Markov chain, right? The Markov chain basically talk about this, okay? The decision making involved only on the previous, okay, is relevant to only the previous status, okay? This type of nature is called the Markov chain, okay? So actually, both Gibbs sampling and the Markov and the Parse algorithm are, Markov chain process, okay? Because in the Parse algorithm, you also jump from the current position, right? You jump from the current position, right? So current position also, has impact to where you must be situated in the next step, right? Okay, so this one, okay, Gibbs sampling is also has this nature. But what's different about Gibbs sampling, okay, relative to the Parse algorithm, is how each step is taken. Okay, so well, let's take 10 minutes break. When we come back, we will continue the discussion here.